And honestly, just like the from them. When I do that for this 1 hour, and then when I do that for this 1 hour, and then
Application-wise, but there's always catch up.
I'm aiming for someone like yeah. So I mean, it's flexible and also I think that's one people are thinking about life. There's no cost. I have to remind it on my own. two in a row now.
The department organised a machine learning talk saying hasn't finished yet. But it wasn't nearly as interesting as this talk's going to be.
Pressure's on.
So Andriy did his master's and his PhD in Toronto. He then went to DeepMind. He was one of the first people to show that multi-layered deep learning really worked. And he's probably going to talk about reinforcement learning.
Almost. It has some applications, but yeah. So it's a pleasure to be here, to have the opportunity to give this talk and to see some familiar faces in the audience. So this talk will be about recent work on implicit reparameterization gradients done jointly with Michael Figurnov and Shakir Mohamed at DeepMind. And this will appear in the upcoming notes. So just to get some sense for your background, how many of you know about variational autoencoders? And I guess reparameterization trick as well? So, excellent. So this will be about extending reparameterization trick to more distributions. So the problem this work concerns with is stochastic estimation of gradients. And this problem has a lot of applications in modern Bayesian deep learning. So things like variational autoencoders and then Bayesian neural networks and so on, as well as some other areas like continuous control in reinforcement learning. And there are two broad classes of approaches to this problem, which is reinforce, as well as reparameterization. And these days, reparameterization is kind of dominant in deep learning. And often for good reason, because it gives you lower variance estimators, which allow you to use larger learning rates and train your models faster, which is obviously a good thing. And the original formulation of reparameterization was kind of tailored to a particular type of distributions where you can kind of factor out the randomness in a particular way. You have some standard source of randomness, like a standard normal distribution, and then you transform it in a smooth way into the distribution that you want, like having some mean and variance. That was very easy to use, but unfortunately it cannot be applied directly to several important types of distributions, like gamma, beta, and so on, where you can factor out this random element. And this work basically is about an alternative approach to reparameterization that allows you to propagate gradients through these kind of distributions while enjoying low variance and so on, without resorting to reinforce. So this is the outline of the talk. I will formalize the stochastic gradient estimation problem, introduce reinforce and reparameterization, and then show how they compare on a couple of two examples, and then review one way of extending reparameterization to more distributions, as well as introduce our approach to doing the same. Stochastic gradient estimators, what are they about? Well, suppose you want to optimize an expectation of some function. We can call it utility or reward. It will be denoted by F here, with respect to some distribution Q. So you have some randomness in your environment or in your model, and you want to optimize for the expected case. So your objective function is the expectation of F under the distribution Q. And we would like to choose parameters of Q in such a way that this expectation is either high or low. But to do this, we need to be able to estimate the gradients of this expectation, and we assume that this is an intractable expectation. So we cannot just compute the closed form expression here and then compute its gradient the way we do with deterministic neural networks. What we would like is to have some sort of stochastic estimator of this gradient where we sample from the distribution, then compute some sort of function g based on this sample, and this function will basically be an unbiased estimate of the gradient of the expectation. And it's important that it's unbiased, which means that in expectation, it's exactly the gradient. Unbiasedness is important because you can always get a system that learns with an unbiased gradient by setting your learning rate sufficiently small. So in a sense, these are well-behaved and well-understood estimators. If your estimator is biased, then the bias does not depend on the learning rate, and so reducing the learning rate does not let you train the system potentially. You might run into some weird behavior, because these estimators are much harder to analyze and understand. So we'll stick to unbiased estimators. So for example, reparameterization gradients for VAEs are unbiased. And as I mentioned before, variance is an important quantity for a gradient estimator, because having low variance for an estimator allows you to use a larger learning rate, which results in faster training. So the lower the variance, the better. And there's a number of modern settings where this kind of problem comes up. So whenever you have an expectation of some objective over some distribution with parameters, you can apply this kind of approach. So for example, in reinforcement learning, you're interested in the expected reward or return over some distribution Q here, which will correspond to your actions in the environment. And in variational inference, you are typically maximizing the evidence lower bound on the marginal log likelihood with respect to the parameters of the variational distribution, which approximates your posterior. So you would like to choose these parameters phi here, so the variational lower bound is as high as possible. So this kind of thing comes up in Bayesian deep learning, in variational autoencoders, variational dropout, Bayesian neural networks, where you perform inference over the parameters by treating them as coming from some distribution, as well as in reinforcement learning, more precisely, I guess, continuous action reinforcement learning, with policy gradient methods and actor critic methods, which are closely related. And then these methods have a really long, but maybe obscure history for machine learning people in fields like computational finance, where they call this sort of thing sensitivity analysis, and in operations research, where they use for queuing theory when you can optimize things like expected waiting time. And there's a lot of interesting work published in these fields, but it's really hard to read because the terminology is completely different. Okay, so let's start with a classic, maybe older estimator. It's a very general one. It's called reinforce. It's an acronym for something that doesn't make a whole lot of sense, but it's a nice acronym. So it's also called score function estimator and the likelihood ratio estimator in like more statistical literature. And this is a very general estimator because it doesn't assume a whole lot. So it just asks you to be able to evaluate your reward function on the samples from your distribution. And if you can do that, you can optimize the expectation, which is, in a sense, kind of remarkable because we are so used to relying on gradients for everything these days. So this estimator basically computes a sample-based gradient estimate by evaluating your reward on the sample Z, and then using it to scale the gradient of the log probability of the sample. So if a sample led to a high reward, you increase its log likelihood more, and if it led to a low reward, you increase it less, and in the end it kind of works out so that higher rewards become more probable, and this leads to optimizing the expectation. So this is nice because it's general. You can apply it to almost any system you can think of. The downside is that it produces high variance gradients. So in its naive form like this, it's really not practical unless your system is really, really simple. And you need to do some sort of variance reduction to make this practical. But if you are careful about your variance reduction methods, then this can be a very useful estimator, especially when you can differentiate F. So this sort of thing comes up in reinforcement learning, often with discrete actions, where basically you can differentiate your reward with respect to discrete actions. So you have to rely on something of this form. And if you speak TensorFlow, this is a way to implement it, kind of to shoehorn it into the computational graph paradigm, where you basically introduce a surrogate loss that when you differentiate it gives you exactly the right gradients. But this is unnecessary to understand for the rest of this talk. So I mentioned the issue of high variance for the reinforced gradient estimator. Fortunately, there's a simple and fairly effective way of reducing this variance, and it's called baseline. And the baseline you can think of as kind of a reward value that you compare the reward that you obtain to. So like kind of like average reward intuitively. So if your reward is higher than average, it makes sense to make this sample that produces reward more likely. And if the reward is lower than average, then you probably want to make it less likely. And one interesting property of a baseline is that if you subtract it from the reward, the expectation of this gradient estimator is exactly the same. So it doesn't affect the expectation, which means that we have the opportunity to choose the value of the baseline to reduce the variance, because the estimator is unbiased no matter which baseline we pick. So then the tricky bit is, how do you pick or estimate this baseline gamma? And please feel free to interrupt if something is not clear. So how do we choose gamma? Well, there's the intuitive way, and then there is the right way. And for many, many years, everyone used the intuitive way, and it was a bit of a shock to discover that this is not optimal. So the intuitive way is, as I suggested, to take the expected reward. So the reward that you get on average, and then compare to that. And often that works pretty well. It turns out that this is not optimal, and in some somewhat unusual settings, you can actually get higher variance by using a baseline like this. So you might be better off not using a baseline than using this intuitive one. But if you're implementing reinforced, this is the first thing to try. It's pretty easy to estimate gamma. You just have some sort of moving average of your reward. The optimal thing, turns out, is more elaborate. It's basically based on the covariance of your gradient with this thing called the score function, divided by the variance of the score function. So you can think of this as a solution to basically 1D linear regression. And this thing explicitly minimizes the variance of the gradients. And this always improves on the variance of baseline-free reinforce. Okay, so here's the other estimator, which is all the rage right now. This is the thing that basically made variational autoencoders possible and so popular. And I guess really popularized Bayesian variational inference. And this is the reparameterization gradient, also known as pathwise gradients in statistics. So here we introduce this concept of a standardization function. And it's a function that takes a sample from your distribution of interest, Q, with some parameters phi, and then transforms this sample in a way to remove all dependence on phi. So if Q is something like a normal with a mean mu and standard deviation sigma, then you can normalize a sample from this distribution by subtracting mu and dividing by sigma. Then you get a sample from standard normal. And this is our goal, to get a sample from a distribution with no parameters. So we will call this distribution Q epsilon. And epsilon will be the normalized version of Z, basically with all dependence on parameters stripped out. So this is easy to do in a bunch of cases, like for a mean scale family of distributions, where you just subtract the mean and divide by the scale. So now we compute the inverse of this function. Now it's S inverse. And this allows us to map the kind of standardized noise source into a sample from the distribution of interest. So this inverts the operation, and now Z depends on phi, because S depends on phi. So this will add mean and scale by standard deviation for epsilon. And now we can rewrite this expectation in terms of a distribution that doesn't depend on phi, so it's Q. And now we push all the dependence on phi inside the argument to F. So now this simply is Z, as we showed here. And the expectation now is with respect to Q of epsilon, which has no parameters. So now differentiating this is very easy, because there are no parameters in the distribution, so we simply take differentiation inside and differentiate the argument, and then use the chain rule. So the first term is the derivative of F with respect to its argument, and then the second term is the derivative of this argument with respect to the parameters. And this is what you do every time you train a variational autoencoder, even if you don't quite think of it in these terms. So if you look at this carefully, this does not quite satisfy the definition of the stochastic gradient estimator we produced before, because it's an expectation over epsilon rather than Z, but this is more of a notation thing, so we can easily fix it. So that's the estimator we got on the previous page. Now let's rewrite it purely in terms of Z. So because this is Z, as we know, we get gradient of f of Z with respect to Z, and this thing we essentially define to be the gradient of Z with respect to phi, because that's essentially the role it performs. And it's defined as follows. This is your inverse mapping differentiated with respect to the parameters. So then our gradient estimator has this form. It's a product of the gradient of f with respect to Z, and then the gradient of Z with respect to phi, just the chain rule. So you can think now of Z as a kind of stochastic differentiable layer you can insert into your computation graph and pretend that it's nothing special and it just trains. So here's an example to make it more concrete. I basically talked about this example, but let's spell it out. So the standardization function for a normal distribution is Z minus mu divided by sigma. That gives us epsilon distributed as the standard normal. And the inverse of it is simply scale epsilon by sigma and add mu back. And now we can compute the derivatives of Z with respect to mu and sigma. With respect to mu, it's just 1. With respect to sigma, it's epsilon, which we can also express in terms of Z, which is just the normalization as we define it here. And now we can write the gradient estimators for mu and sigma in terms of Z alone without any reference to epsilon. Okay, so let's see how reparameterization compares to reinforce. So this is kind of a confirmation bias example. We have an objective that's a square of Z, which is sampled from a normal distribution with mean mu and sigma squared. We set sigma to 1, and then vary mu on the x-axis here. And we look at the gradient of mu at that point, and the gradient of sigma at that point of this expression. This is our objective. So the purple line is the variance. So this is variance. This is variance of the gradient. And this is variance for reparameterization. As you can see, it's lower than any version of reinforce. It's basically the same because the gradient was 1. And depending whether you use intuitive baseline, the mean baseline, or the optimal baseline, you get lower variance for reinforce, but it's still a long way to go to reparameterization. And then for the gradient with respect to sigma, the story is fairly similar, except that now the variance of the reparameterization gradient actually depends on mu. So this is what you kind of, this is the old wisdom, like reinforce is bad, just avoid it at all costs. So to complicate the matters, here's another example. Now we have a different f that we are computing the expectation of. So the distribution is exactly the same. It's normal with mean 0 and variance of 1. But the objective now is exponent of minus kz squared. And k is a free parameter we choose. So k will basically define the problem we're interested in. And depending on the value of k, the problem will actually be easier for reinforce or for reparameterization. So if k is small, f looks like this. It's a fairly smooth function. As you increase k, it becomes more and more concentrated around 0. So you can think of it as an unnormalized Gaussian, constrained to be between 0 and 1. So basically, as you increase k, you basically end up with like a spike at the origin. And perhaps surprisingly, the story is very different now. So for a small value of k, the story is similar to the previous slide. Reparameterization is better. But as you increase k, the variance of the reparameterization gradient goes up a lot. And then it becomes much higher than the variance for any of the reinforced estimators, including the one without the baseline. So basically, and the story is similar for the other parameter here. So I think the intuitive way to understand this is if you have a function where you have rapid changes in the gradient, like high points of very high curvature sometimes, gradient is actually not very informative. So if you're averaging a bunch of these gradients, you get a high variance estimator. So for example, if you think about, if you differentiate this term, you will have minus 2kz in front of it for the reparameterization gradient, which scales the gradient by a value which might potentially be large because k is increasing. But for reinforce, this term, it stays the same, and k just actually makes this multiplier smaller. So the variance goes down. So you have to be careful assuming these things. But in normal cases, try reparameterization first and see if it works well enough for you. Okay, so reparameterization seems like a very useful tool. What are the limitations? Well, it's applicable only to continuous distributions because you need to somehow factor out this randomness in a way that's connected to the original sample using a differentiable function. So you can factor out randomness in the discrete case as well, but the function involved will not be differentiable. So then averaging those gradients will not be useful. So you cannot apply to discrete variables. So there are alternative approaches. You can relax your discrete variables to continuous ones to approximate your objective. You will not be quite optimizing the right thing, but it can work surprisingly well. So like concrete relaxation, which Chris Madison talked about in this seminar a few months back, is one type. And you can also use reinforced-based methods with various variance reduction techniques, which can also be effective. And then the other limitation is that for some continuous distributions, it's still not straightforward to find a function that removes dependence on parameters in a differentiable way. So for Gaussian, it's super easy, but for something like gamma, no one has been able to figure that out. So can we address this second limitation and essentially be able to reparameterize any continuous distribution? Yes?
Would you say the distribution flow helped with the second problem, with the limited scope? Distribution flow, or the normalizing flows?
Yes, okay, I see. So basically if you apply, it depends what you call Z in your setting, and where you draw the circle, and on which variable you perform inference or gradient estimation. And I think you're right, so you can basically start with some standardized distribution like Gaussian, and then use flow to deform it into something more like what you're interested in. I'm not quite sure what the trade-off would be there, but yeah, that's an interesting solution, yeah. Good point. Right, so let's look at ways of extending applicability. And first of all, let's look at some distributions where you can't apply standard reparameterization. So the first one is von Mises. And this one intuitively is essentially a Gaussian in a circle. So if you have a point in a circle and you would like to say that your samples come somewhere from that region, there will be a unimodal distribution centered at that location with some standard deviation. So if you put a Gaussian in a circle and wrap it around infinitely many times, this is von Mises. And it's used for like directional statistics and so on. So it's really not straightforward how to break out the dependence on Z here with a continuous reparameterization. The other notably absent distribution is gamma. So if you're doing Bayesian analysis, this is conjugate prior for the normal precision. So this is very much missed from the statistical toolbox, as well as any kind of distribution that can be constructed from gamma. So like Dirichlet can be easily constructed out of gammas. So if you have a way to reparameterize gamma, you can reparameterize Dirichlet, beta, and so on. But once again, it's unclear how to reparameterize this using the standard approach. And as I mentioned before, Dirichlet, which is useful for topic modeling and so on. Okay. Okay, so one existing approach for extending reparameterization is basically by combining reinforce with reparameterization. So the basic idea is as follows. Suppose we don't know how to backpropagate or compute gradients with respect to Z, where Z is our distribution of interest. But let's come up with some distribution that's not very different from Q, which we can reparameterize. So you can start with a normal and then warp it somehow. Maybe you can apply flow, for example. And if you can reparameterize that distribution, it will give you some gradients, but these are not the right gradients. So then you correct for the fact that you're using the wrong gradients with a reinforced term. You can think of this essentially like using importance sampling to correct for the discrepancy. So your gradient estimator ends up looking like this. This is essentially reparameterization gradients for the wrong distribution, for the approximating one. And this is the reinforced term that corrects for the bias in these gradients to make sure that they are unbiased for your distribution of interest. So this is quite ingenious, but this raises some questions. So first of all, are you getting very high gradient variance because of this term? And how do you choose this approximating distribution? So there are two methods for doing this, both from David Bly's lab, and they're very similar. So the high-level description is basically the same as on the previous slide. They differ in how they choose this approximating distribution. So the generalized reparameterization gradients approach says, okay, let's take a standardizing function, but we will not look for removing all dependence on the parameters of the distribution. Let's make the mean and the variance, for example, not depend on them, and then the higher moments will depend on these parameters. Or maybe just the mean if you can't figure out variance. Of course, the trade-off will be the less dependence you remove, the larger contribution from the reinforced term will be, and the higher the gradient variance. And then there's the other approach called reparameterization gradients through rejection sampling. And here you take an existing method for sampling from your distribution of interest. So like if you have a gamma distribution, there is a rejection sampler that generates samples from it. And it starts with some continuous proposal from which you can sample, usually a transformation of a Gaussian or a uniform, made to look like a gamma distribution, but not quite perfectly. And then you have the accept-reject step to make sure that you get samples from exactly the right distribution. And they basically treat the proposal distribution as that R, that approximated distribution, and they derive a way to backpropagate through this process. And that gives you this kind of reparameterization plus reinforce estimator. And once again, like the more effective your sampler is, the less contribution there will be from the reinforced gradient. And the nice thing is you can use the existing sampling methods. Okay, so let's see if we can avoid the reinforced term altogether. Can we actually have a pure reparameterization approach to this problem somehow? Well, let's think about the setup. So the standardization function, you have to find it somehow. So one universal choice for univariate continuous distributions is simply the CDF. Because if you take the CDF, apply it to a sample from your distribution, it will return a sample from the uniform over 0, 1. So by definition, this strips out any dependence on the parameters. So that's something you already have generally. Your framework for training deep models typically has some implementation of the CDF. The problem is that if you want to apply the standard reparameterization, you need to invert the CDF because we're working with the inverse standardization function, which is already harder. You don't always get inverse CDF. And then you need to compute gradients with it. So that's potentially problematic. Like for example, for a gamma distribution, the CDF looks like this. This is an intractable integral. And inverting it, basically you could try a root finding method, which is complicated and probably depends on the exact sample value, what kind of precision you want. Or you can use finite differences, but that potentially is also error prone. And it is biased. So can we somehow avoid inverting the CDF altogether? I'll keep you in suspense for one slide, but something completely random. Let's review implicit differentiation. So implicit differentiation allows you to compute a derivative of a function that's defined implicitly. So here we have a function y of x, and it's defined using this equation. X squared plus y squared is 5. So basically all points that satisfy this equation and are greater than 0 defines a function. For different values of phi, we get different functions. Let's compute the derivative of y with respect to phi. So there's the kind of brute force way of doing this. We can first solve for y, getting this, and then just differentiate it. This would be the equivalent of essentially inverting the CDF in the previous example. But let's try something else. Let's do implicit differentiation. Let's differentiate both sides of the equation with respect to phi, keeping in mind how dependence on phi propagates. So x is a free variable here. It doesn't depend on phi. So its derivative is 0. But y depends on phi. So then we need to apply a chain rule. So we get 2y, and then derivative of y with respect to phi. This is equal to 1, because we differentiate phi here with respect to phi. And then we solve for the derivative of phi, which is just 1 over 2y. So here we have an expression for the derivative of y with respect to phi that does not involve x. And this gives us some hope, because this is the equivalent of working with the CDF directly without having to invert it. So let's see if we can apply the same trick to the reparameterization setting. So here's our standardization equation. Let's differentiate both sides with respect to phi. So epsilon doesn't depend on phi by definition, so it's 0. S depends on phi in 2 ways. First, directly through its parameters. So then we apply the chain rule as before. And secondly, because Z is a sample from a distribution that's parameterized with phi. So there's also dependence on, this is the term that captures the dependence through Z, chain rule. And here it's just a direct dependence on phi. Now we are interested in this term. Well, we just do some linear algebra. We solve for it, and this is just this. So we don't need to invert the CDF now. We invert a matrix. So basically, we're doing linear algebra instead of something more complicated, potentially involving symbolic computation. So now we basically solve an inversion, or solve a system of linear equations, and we get our gradient. Easy. So let's look at this in one dimension. So if our standardization function is the CDF, U will be uniform, which used to be epsilon. So now we rewrite the expression from the previous slide in one dimension. So this is the derivative of the CDF with respect to the parameters. And this is simply the derivative of the CDF with respect to Z, which is simply the density for a continuous, nicely behaved function. So now the tricky bit is simply computing the derivative of the CDF. And sometimes it's provided. And if not, we can simply take the code that computes the CDF and perform forward mode differentiation. So if the CDF is computed in like I say, a computation graph in TensorFlow, TensorFlow will do this for you. Alternatively, you need to find someone like Michael Figurnov who will go through the code and add the forward mode differentiation to it. And then you've got your derivative. Now suppose you have a multivariate case. Is there a kind of a mechanical recipe for computing the derivatives? Well, we can define standardization essentially using conditional distribution. So it's exactly this idea, applied to one dimension at a time, conditioning on the previous dimensions we have already standardized. So the first dimension of the distribution, we apply the CDF. The second one, we apply the CDF, conditioned on the first sample, and so on. So this is basically a chain rule of probability. And then we get a vector of uniform random numbers. So this is just one way of doing it, kind of like a universal way, but perhaps there is a better way to find a standardizing function for the distribution of interest to you. So it might be worth thinking about whether there's a better solution to this. Like for example, when you're dealing with a Gaussian, well, you don't need to use implicit differentiation for that, but for example, you probably don't want to use a CDF for a Gaussian because there is an easier way. So maybe your distribution also has some easier way of doing this. Okay, so let's compare explicit reparameterization, the one using BAs and so on, to implicit reparameterization. So what are the key differences? Well, first of all, it's a sampling process. For explicit reparameterization, you generate a sample from some standardized distribution, and then you transform it into the distribution of interest, and then essentially use automatic differentiation to propagate the gradients through this by differentiating S. So it's denoted here. In implicit reparameterization, we're essentially decoupling the two steps. We have some way of sampling from the distribution, which is a black box. We don't need to know how it happens. And then once we get a sample Z from the distribution, we don't need to know epsilon. We simply use the standardizing function and solve that linear system. And that gives us the gradients. And then we use them in exactly the same way in the chain rule. That's it. So I think the important idea here is this, that you can actually decouple sampling from a gradient estimation, which is a bit, maybe slightly counterintuitive or unusual in the world of these end-to-end differentiable computation graphs. On the other hand, once someone did this for a distribution, made like a layer that implements this, you don't need to know about this. You just plug in this distribution into your computation graph, and everything works automatically. So which distributions can this be applied to? Well, quite a few. So this can be applied to multivariate mixture distributions, truncated distributions, gamma and its derivatives. So once you have gamma, these can be constructed from gamma and von Mises. So Michael Figurnov implemented most of these, and now they're available in TensorFlow and TensorFlow probability. So now you can just use these distributions without having to know any of this. The gradients will be correct. Like most ideas, this one is not completely novel. So once we put this on archive, we learned a few things. For example, there's a paper from 1988 that has both explicit and implicit reparameterization. And it's from operations research. It's quite obscure, but someone did this in '88. And the system is very simple, one-dimensional, but it was there all along. I guess if you know what to read. And then there was some other work on this in machine learning with various simplified cases of this setup. The most related work is from actually Uber, from Jankowiak and Obermeier from ICML this year. And this was concurrent work They have a slightly different approach and they concentrate on gamma. We'll compare it to it in the experiments. And so our explicit contribution is we basically generalize the approach to any standardization function, not just CDFs. We show the exact relationship to explicit reparameterization, how these two map to each other. And we show how you can use automatic differentiation so that you don't really need to think about computing these derivatives, and you don't need to use any kind of approximations.
Yes. Question. So what kind of condition do you need for that distribution? So for example, if CDF becomes flat for some region, you need to take inverse of this, right?
So if it's the region, so if it's kind of external region, so for example, for a beta distribution, the CDF is like 0, well, it's flat outside 0 to 1, so that works just fine. But if you have like a flat region inside the interval of interest, you can't exclude it easily, then it's a problem. But I'm a bit hard pressed to think of a non-contrived example of this. Yeah, but there might be a question of gradient variance, like the distribution has like very high slope or something like that. The usual trade-off, gradients, reparameterization gradients versus reinforced. But I think that's it's hard to avoid that. Yeah. So here's just kind of a small sanity check to compare our approach, which here we denote automatic differentiation, to using finite differences, which is a really easy way of computing gradients. It's biased, but it's easy to implement. You basically evaluate the function at 2 points and then approximate the derivative based on the difference. So, that's how the derivatives are defined in calculus in the limit of the step size going to 0. But the step size has to be small enough to have good accuracy. And then there's the method from the Uber paper based on truncation of the gamma CDF to some number of terms, which makes it easier to estimate gradients. And then a finite difference-based approach from nulls. So basically, our approach is both faster and more accurate than all of these. And for von Mises, there was basically no existing counterpart of this step. So it outperforms finite differences quite considerably, but you can actually get away with finite differences if you're willing to use higher precision. So if you want float 32 precision and you can afford computation in float 64, finite differences will give you a comparable precision to our method, but this is more expensive, and on some devices like GPUs, this is not always available or as fast. Okay, so a slightly more elaborate example. Let's look at estimating the gradients of cross entropy between our distribution of interest Q and some target distribution P. P will be, both Q and P will be factorial. Okay, it will be factorial here. Here it will be Dirichlet. And Q is different from P in one parameter. This is just the parameter we would like to estimate the gradient for. And we compare our method to rejection sampling variational inference, which is the more effective of the two reparameterized plus reinforced methods. And for gamma, there's a trick where you can trade off computation versus using the reinforced term less. And basically, it involves augmentation through generating more random numbers, essentially. And as you expect, as you augment rejection sampling more, spending more computation, the gradient variance approaches implicit reparameterization. But even for no augmentation, implicit reparameterization is faster. So it seems like an easy choice here. For a distribution like von Mises, there's no augmentation trick known. So you don't have this trade-off, and the difference in gradient variance is quite considerable. Okay, so a larger scale experiment, latent Dirichlet allocation. This is a classic latent variable model, which was basically the model for doing variational inference before VAEs came along. And it's basically a topic model that models documents as bags of words, which is like vectors of word counts. And each document is represented as a distribution over topics, which is modeled as Dirichlet. So to generate a document, you sample a distribution over topics. And then for each word, you sample a topic. And then you pick a word from the distribution for that particular topic. So the hope is that the model will figure out that documents usually use only a handful of topics and determine how many topics there are in this corpus. And we will train this model in a VAE style, so we'll use amortized inference. So we'll have a neural network parameterizing the variational posterior, which we will parameterize as Dirichlet. which is the usual approach for LDA inference. And we'll optimize it by maximizing the elbow, which is the classic approach. So using DAE-like inference on a model like this was non-trivial until recently because you couldn't reparameterize Dirichlet. So there was work from Srinivastava and Sutton in Edinburgh based on a proxy distribution. So because they couldn't deal with Dirichlet, they replaced it with some proxy. So they basically said, we'll have multivariate normal, and then we'll pass it through a softmax. And there you have a distribution that adds up to 1. So that's a reasonable replacement. And then this you can reparameterize because you can reparameterize normal. And then you perform amortized variational inference using this setup. But you'll see that there's a downside to this. So let's compare our approach to rejection sampling variational inference with different augmentation levels, as well as this proxy-based method with explicit reparameterization. So on the smaller data set, basically all methods, once you use enough augmentation, perform about the same. But on the larger data set, implicit reparameterization performs best. And once you augment the rejection sampling variational inference enough, you get comparable performance. So I should say, in theory, all unbiased estimators are the same in the sense that if you use a low enough learning rate, you should get a similar solution, ignoring local minima issues. But in practice, you need to find a learning rate and enough patience to do that. So you do some sort of hyperparameter search, and given your computation budget, you can only do so much with given gradient variance level. And basically, these are the solutions we found using Bayesian optimization. And as you kind of expect, looking at the gradient variance plots, implicit reparameterization is at the bottom, and as you increase the augmentation level and computation cost for rejection sampling variational inference, you eventually match it with 20 samples, which is considerably more expensive. And here's an example why using proxy distributions is not always a good idea. So one nice property of the Dirichlet distribution is that it can encode sparse distributions. So it can basically say distributions coming from Dirichlet will have a few topics with high probability and most other topics with low probability. So you will basically have a document that will reference maybe 3-4 topics, everything else is negligible. And this is a nice property to have because it allows you to understand the data better. But when you use a proxy distribution like multivariate Gaussian pass-through softmax, it's a unimodal distribution, so you cannot have this sparsity property. And as a result, you can't really learn these sparse distributions. So this is basically the distribution of topics under the prior in the trained LDA model. And when you use like strict LDA with Dirichlet trait using implicit reparameterization, the model discovers that you have about 10 topics in this fairly small data set, and the other topics are not useful. For a larger data set, it uses 30 topics and discards the rest, while the proxy-based LDA essentially uses all topics to some degree. And if you look at the topics discovered, the proxy-based LDA essentially replicates many topics multiple times, which makes the model not very useful for understanding the data, because what does the topic mean if it's the same as another topic? There's a considerable difference between topics in LDA trained using a Dirichlet test theory. And finally, an example of a variational autoencoder trained using a von Mises distribution in the latent space. There should be a plot of gradient variance here. And trust me, implicit is lower. But here's the thing you ultimately care about. This is performance as a function of time as you use Adam optimizer. And you can see using implicit reparameterization leads to faster training. One of the reasons is that Adam normalizes the gradient by an estimate of the variance, or standard deviation. So whenever your gradient is noisy, Adam automatically reduces the learning rate. So it pays to actually have low variance gradients, and it translates into better performance for a given computational budget. So that's the plot I promised. Much better. And finally, because we can deal with many distributions, we do something relatively exotic and take a DAE and use non-Gaussian distributions for the prior and the posterior. So this is the two-dimensional latent space on MNIST if you use the usual setup with normal prior and posterior. And you can see that most of the interesting stuff here happens in the middle. The boundaries are kind of boring. it doesn't use that much of the latent space. But if we use a uniform prior and then a beta posterior or a von Mises posterior, you get very different latent space topology. So beta distribution is 0, 1, and it uses this interval a lot more. So you can see that it models the slant of the digits here, and then the digit type along this axis. And with von Mises posterior, because it's a distribution in a circle, the latent space ends up being periodic. So you end up with 7, 9s, and 4s here and here. So if you think your latent factor should have topology like this, it makes sense to use latent variables from the right distribution. And now you don't have to work very hard to do that because it's just implemented by someone for you. So to conclude, we introduced implicit reparameterization gradients, which extend reparameterization to many new distributions. Some highly useful ones like gamma, von Mises, and Dirichlet, and so on. And now it's part of TensorFlow, and at least gamma is already part of Torch. So it's only a matter of time before these are kind of very standard primitives. So you just think of these as options when you're building your stochastic computation graphs for your models. And our particular approach has lower variance than the computing approach, so it translates into faster optimization. If now you have the choice of not making modeling decisions based on computational convenience, and take advantage of that. Thank you. So, questions? Yes.
Do you think this approach has any application for like discrete random variables for improving the variances of those estimators?
Not in its current form, but there is, I guess, a class sounds too grand. There's a couple of gradient estimators for discrete latent variables that use relaxations under the hood for variance reduction. So maybe there's room for looking for some other types of relaxations that might provide, nothing immediately comes to mind, but maybe it's an interesting direction. Yeah.
I have a question.
Yeah.
So for gamma distribution, to compute CDF, you need to compute the inverse of the gamma function. How do you compute the derivative of the gamma function? With respect to the input.
Respect to the input. Basically, you take the code. So we need the code that computes the CDF,
Right.
Whatever that involves. And then for each step, you add code that computes the gradient of this result with respect to the parameter of interest. Like this is a fairly mechanical procedure. It's painstaking, but like if you have the code and you have essentially a lookup table of what derivative is like, that's it. And if you use TensorFlow, you don't have to think about that. But yeah, it's not straightforward in the sense it's hard not to make a mistake, but it's mechanical in the sense that it doesn't require creativity. So it's a matter of time of implementing it. Yeah,
Right.
testing it carefully.
Okay. And do you know the typical tricks that people use in TensorFlow to compute CDF when they come to integrals? Do they use?
I think they usually use like infinite series expansion, and then like stop once the precision is high enough. And I think this is essentially what's been done. Yeah.
So do you think that also introduce biases?
I mean, yes, in this, well, if you go that route, then basically you're never computing the true gamma function anyway, so yes. I mean, everything is biased in a digital computer, right? Yes.
So you showed at one point that explicit reparameterization can sometimes have worse variance properties than we enforce, and I'm curious about how that relates to implicit reparameterization. Well, are there conditions under which implicit reparameterization will also be worse than implicit?
So that's a very good question. So there's a slide that I kind of hit at the end. So it's related to this. So in one dimension, if there's a distribution, you can reparameterize in the explicit way and the implicit way. If it's one dimensional, the gradient estimator will be exactly the same. So there's no room for maneuvering there. So if the old gradient is high variance, this one will be high variance. But in high dimensions, this is not true. So there is room for creativity and innovation. So depending on how you normalize it, like in which order, for example, you might be able to get a lower variance gradient. So then you can use that for variance reduction. So there's an interesting paper another paper from Uber, from Jankowiak and Karolitsas, which is on arXiv, pairwise derivatives to multivariate distributions. and they're looking at ways of getting lower variance for multivariate normal by taking advantage of this. But unless you're a physicist, good luck with that paper. It's very interesting, but it's like not easy to read. Yes?
Sort of a naive question, I guess. Does this technique have any particular, do you have any particular insights to how this technique might behave in the case where you have chosen the wrong distribution? You know, you get it might be like robustness in cases where the distribution might not actually match up.
So that seems to be more of a modeling question. So the stuff was entirely, you give me an expectation objective and then, you know, I do something to it. If you're using the wrong Q, yeah, I think that's a different question. Yeah, it's an important one. Yes?
So do you think in your how to reparameterize case, you apply something like contrastive divergence to approximate gradient? Because I think in that case, you have a kind of both partition function to approximate using sampling, and then you get a estimator of gradient.
So I guess contrastive divergence in a sense is like truncated MCMC sampling, right? I think it would relate. So there's a weight. So I mentioned that there's a finite difference method of estimating gradients, and it's reasonable in one dimension, but as you go to high dimensions, it doesn't scale well because it's basically exponential law. And there's a way of trading variance for computation efficiency by using randomization and picking direction for your finite differences. And I think this is probably the closest reference point that I can think of to contrastive divergence. Because here, there's no explicit normalization that I can think of, so I'm not sure how to map it otherwise. But you can use kind of this randomized directional derivatives to estimate gradients. But you will get higher variance as a result, because you're using unnecessary sampling.
So regarding the trade-off between like reparameterization and then reinforced, can you go back to your slides of the inverse of your CDF with respect to Z, derivative of CDF with respect to Z?
So the
Right.
Here or another one? Like this?
Yes.
Okay.
Oh, so can you go maybe like 2 sides forward?
Maybe backwards? Or
Oh, even just this one right here.
Okay.
So, so if you look at this formula, it's intuitively, when you compute the inverse of the inverse term, so that which is the gradient of the CDF with respect to the input of the CDF, which is the random variable.
yeah.
So if it just so happen that you sample a random variable from very low probability region, this term will be infinite.
Well, I mean, it has to be sufficiently high to sample from there, right?
Right.
It can be large, right?
Right. I'm just saying, if you got unlucky of sampling those points.
But as I pointed out before, like in one dimension, this is what the other reparameterization would do. You just probably wouldn't be horrified by it because you didn't see the inversion there. But maybe the inverse CDF actually is the equivalent.
Right.
So like if you're in the tail, it's going to be.
Right. But then if you use a reinforced algorithm, even if you sample from a very low probability region, you will still just look at your reward.
Yeah.
So you actually bypass this problem of having like very large gradient.
Yes, I agree. So I think like if your objective function is like piecewise constant or something like that, or there are like these big jumps in density, I think reinforced would actually excel in those regions. So,
right.
And now there's work combining these different estimators in a way to minimize variance, which is quite interesting. Basically, you need to keep track which one is working better right now, and then basically blend the gradients appropriately. But you probably want someone else to do it for you. Any more questions?
All right, let's thanks Andriy for his talk. And lunch will be served outside and help us out.
Thank you. Yeah. I was really hoping. No, I was hoping you would. You know, like. Well, you know, I've been speaking for a lot of people, so I was wondering what you guys like. Well, I hope this was a bit more because Reparameterization all kinds of both. No. Yeah, but then we can all adjust that. Yeah, I think doing anything real. Yeah, no. Abstraction, right? To a point. Have you seen the gradient expression? At one point, that's what we can propose, but yeah, exactly. The thinker was very useful, so I respond to it. Yes. Tomorrow, no particular.
Try to like catalog like research.
Yeah, sounds good. Yeah. Okay. All right. See you then.
Right. Yeah.
That's right.
Yes.
Right.
This?
Oh, you did.
This is simply dividing by 3. It's just like a little longer.
Right. What does that mean? That's like, I guess every instance is like, so every region has like, because like,
Those are x. Yeah, so x and minus log.
if the CDF is flat, it will
X and log cancel out, and minus
PDF is flat, right? It's like you're writing down division no gradient, and then you make everything flat in the CDF, but so you're creating like 6 actually.
Well, that's what you say.
So this is just a way of writing.
Oh yeah, that's right. Right.
Yeah, but that's right. I think it's not. I think it's merely expressing this division locally. I think also, I mean, in the worst case, you can always look at the tensor. But hopefully, it won't go. Yeah. So like email like if you have a question like he's super helpful. He did all the hard work. So. Yeah. I think that's what I mean.
Happening for the I minus the Jacobian, right?